In this session, we're going to talk about the relationship between the standard cell potential and K, the equilibrium constant. So, in the same way that we could use the Nernst equation to calculate the cell potential under non-standard conditions using log of Q, so if Q equals K, okay, so then the system is at equilibrium. When Q equals K, then the cell potential equals 0. So at equilibrium, the reaction is not spontaneous in either the forward or the reverse direction. There's no potential energy, nothing happens. So if we substitute in log K for Q and 0 for the cell potential, then we find that there's a relationship between K and the standard potential. So then we can use either of those to calculate the other one. And if we plot the relationship between K and potential, we see that cell potentials really only range between about -3 and +3 volts. Most of them are kind of there in between -1 and 1. That said, if we see how that would affect K, we end up with a really, really wide range of K values. So small changes in potential result in large changes in K, and that's what that log relationship is showing us. What that means is that redox reactions tend to go to completion, or they don't go at all. So they have either really large or really small K values. There aren't a whole lot right in the middle. So we could calculate the equilibrium constant for this reaction. We've looked at this electrochemical cell several times now. And so if we want to calculate K, then we know that we can use the standard potential times 0.0592 volts divided by the number of electrons transferred times log of K. That will get us there. So here, our standard cell potential is 0.46 volts. We've calculated this a couple times before, and we know that we could find it using the standard reduction potentials. And we know that the number of electrons transferred here is 2. So if we rearrange all of that, we get K equals 10 to the, so we get rid of the log, 10 to the power of 0.46 divided by 0.0592 divided by 2. All right, if we do that, we get 3.5 times 10 to the 15. Okay, so we see that this reaction very strongly favors the products, and we can calculate the value of K. So we find that we actually have a lot of different ways to calculate K. So in this class, you've learned that you can use delta G to calculate K, and you can use this, we just learned you can use the cell potential to calculate K, and then remember you can use delta G to calculate the cell potential or vice versa. So if you have any one of those quantities, you can calculate the other two. Delta G and K and cell potential all tell us about the spontaneity of a reaction.